Okay, I think we'll make a start. Thank you to everyone who's joined us for this interactive stakeholder engagement session for the Gracious project. I'd like to start by repeating my request earlier on to place in the chat any comments that you have about nanomaterials that you're currently interested in, any routes of exposure that are relevant to you for humans or environmental compartments that you think are a priority. And if you put that information into the chat, then we can use this to help us guide the discussion later in this session. So I'm Vicky Stone. I'm the coordinator of the Gracious project, and I will start this session today by providing you with an introduction to the Gracious project and the framework before I hand on to some of my colleagues to give you more detail about some of the parts of the framework and the project. Sorry, there we go. Okay, so welcome to this event today. We've got 3 events on this week for stakeholders. So if you're interested to know more about the other ones, you can find out after our event today. But my presentation today is going to focus on describing to you the Gracious framework, the integrated approaches to testing and assessment. I'm going to give you an introduction to these. These are the tools that we use to gather the information required to justify or provide the evidence needed to support grouping hypotheses that are used to formulate reasons why you can group nanomaterials together, and the different formats of the Gracious framework that are available to you. And I'll also describe to you some of the key impacts of the Gracious project that have been achieved so far. So the Gracious project started in January 2018 and it will finish later this month. We have 23 partners across Europe and 2 in the US. And the aim of the project was to make a framework which would support users to group different nanomaterials together in order to streamline the risk assessment process, and specifically to support read across of data from nanomaterials that contain the data required for risk assessment to those nanomaterials that lack that data. Throughout the framework, we have used the term nanoforms to represent different types of nanomaterials. So a nanomaterial might be, for example, titanium dioxide, whereas a nanoform might be titanium dioxides of different sizes, shapes, and with different coatings. So conventionally, when we conduct risk assessment, we do this on a case-by-case basis, but this approach is very expensive, it's time-consuming, and it uses large numbers of animals. By grouping similar substances together or similar nanoforms together, you can streamline the risk assessment process. But you need to make sure that they are sufficiently similar in terms of their physicochemical characteristics, their toxicology, and their ecotoxicology. And this is outlined in regulations such as the European Chemicals Regulation REACH. Gracious provides users with a framework to support the assessment of similarity and therefore grouping. And these methods provided in the framework are either qualitative, but also quantitative. And these quantitative methods are very useful for regulatory applications of grouping and read across. The framework was generated early on in the project. It was shared with stakeholders from policymakers, regulators, industry, nationally, internationally. And we gathered lots of feedback from these stakeholders in a variety of formats in order to allow us to refine the framework. This framework was published in Nano Today in 2020. So here we have a simple version of the Gracious framework, which starts with entry using either a single nanoform for which you lack the data required for risk assessment. And so you want to identify whether a group exists that nanoform could be incorporated into. Or you have a provisional group of nanoforms, some of which contain the data for risk assessment and some of which lack that data. There is then a basic information step where you gather some information that allows you to generate a grouping hypothesis. This hypothesis provides the scientific reasoning for you to group those nanoforms together, and a hypothesis is required by the European Chemicals Agency for regulatory applications of grouping and read across. You then need to gather the evidence to support your hypothesis, and this is achieved using IATAs, or integrated approaches to testing and assessment. And these IATAs use tiered testing to allow you to use a range of different method types and model types to gather the evidence, either existing evidence or new evidence, to support the grouping of your nanoforms, to refine the grouping hypothesis if the hypothesis is not appropriate, or to conduct a risk assessment on a case-by-case basis. So I've already said that the framework is suitable for supporting regulatory applications of grouping and read across, but we've also made it sufficiently flexible so that it can support innovation or safe by design approaches. It can also provide refinement of testing strategies, and it can also help individuals to identify precautionary measures to reduce risks, either in an occupational or a consumer exposure scenario. So this is a more detailed version of the same framework. So again, you can enter with a single nanoform or a provisional group of nanoforms. And this time we have some detail about the basic starting information. It includes the physical and chemical characteristics. These are just 4 phys-chem characteristics, such as size, shape, composition, and surface coating. And these can be estimated values, for example, during the early design phases, or known values if you're going for a regulatory application. We also need information on the release and exposure of these nanoforms. Again, these can be estimated or known. And this is required to help us understand the most relevant exposure routes for humans, or the most relevant environmental compartment. And we also need you to identify the purpose of grouping so that we can work out whether you should be using estimated or known values, and the level of detail that's required in this more detailed phase or step of the framework. Once you've gathered this basic starting information, you can then identify the most appropriate grouping hypothesis. The framework is populated with 40 predefined hypotheses. These have been generated by the partners of the Gracious project based upon peer-reviewed literature and the generation of new data. If these predefined hypotheses are not suitable for your application, then you can make your own user-defined hypothesis, and we've provided a template to help you do this. Once you have a hypothesis, you need to test that hypothesis, and it's tested via using these integrated approaches to testing and assessment, which use existing information, model information, or testing where required. The outputs of your tailored IATA are to just generate the data that you absolutely need to test your hypothesis, and then that data is inputted into a data matrix, and that data matrix allows you to compile all of the evidence for all of your potential candidates in your group side by side so that you can conduct a similarity assessment, and that data matrix is required for regulatory applications in particular. So once you have your data matrix and you can conduct your similarity assessment, you can either decide that your grouping is justified and go on to conduct activities such as read across, or you can refine your hypothesis and go through this process again, gathering more information if required, or you may decide that grouping is not appropriate and you therefore conduct testing on a case-by-case basis. Once you've gathered your group and the information required to justify your grouping, you can look at the candidate nanoforms within your group. Some of them should be lacking data. These are your target nanoforms. And some of the components or candidates within your group should have the data required for risk assessment. And we call these our source substances. And they may be a nanoform, or they may be a non-nanoform in some situations. You use the grouping hypothesis for this group to formulate the wording required for a read across hypothesis. Use the data matrix that you already have for your group to make sure you have the information required to justify your read across hypothesis. And then that allows you to amass all the information to justify your read across from the source substance to your target nanoforms. I've mentioned that the framework can be used during innovation and safe by design. And you can see this basic information step here maps onto the early stages of the innovation process. If innovation goes from discovery through to launch, going through these 5 different gates here. So the basic information maps onto the earlier stages, whereas the detailed step can take you right up to the launch of your product, including the regulatory requirements for that product. So as I said, we have a hypothesis template. This has been used already to generate predefined hypotheses. We have 17 for human hazard and 23 for the environment. If you want to use the hypothesis template yourself, you need to provide information on what they are. So that's the physical and chemical characteristics. Where they go, so that's where they go in the body or where they go in the environment, and then what they do, so they're hazards either to human health or to other species. And this needs to be all considered in the context of specific life cycle stages, so whether it's the pristine product during the manufacturing process or the product used by a consumer. And it also needs to be thought of in the context of the purpose of why you want to do the grouping and the context in which the nanomaterial is being used. So here are a couple of examples of some hypotheses that we've generated. The first one is for human health. It covers the inhalation route of exposure, and it focuses on quickly dissolving nanoforms. And it suggests that following inhalation, both nanoforms and the constituent ions or molecules may contribute to the toxicity, but there's no concern for accumulation. But the toxicity may depend on the location of the release of the ionic or molecular components. For the environmental hypothesis, we've chosen one here that relates to coated nanoforms. And here it suggests if the chemical coating is lost from the nanoform in the soil compartment, then if similar nanoforms lose their coating, then they can be grouped. And in fact, you could read across to a non-coated analogous nanoform in that compartment. So as well as having respiratory hypotheses, we have hypotheses for the gastrointestinal tract and for dermal routes of exposure. And we have environmental hypotheses for aquatic, sediment and soil exposure as well. So these hypotheses are tested via these or evidenced by these integrated approaches to testing and assessment. So these compile together existing information and newly generated information as required. And they consist of a series of decision nodes or questions. And these decision nodes allow you to gather the evidence required via tiered testing strategies, usually consisting of standard operating procedures such as OECD test guidelines. By answering yes to each question, you accept your grouping hypothesis. If at any point you answer no to a question, then your hypothesis is rejected. To allow you to answer a question yes or no, you may need a threshold, but thresholds are very difficult to justify scientifically. And so we've also provided a range of methods to allow you to assess similarity. And this means, therefore, if your value is close to a threshold, if you have a similarity method instead, you don't need to worry about sticking to that threshold value or even generating a threshold in the first place. Once you've gone through all of the decision nodes for your IATA, this allows you to populate your data matrix. So if we think about a single decision node within the IATA, for every decision node, there is a tiered testing strategy where tier 1 would be simple methods such as in silico, in chemico, or in vitro methods, whereas tier 3 might be animal models for the human case or maybe a mesocosm study for an environmental case. Safe by design applications for the framework could often depend on tier 1 methods, but if there's too much uncertainty for a tier 1 method, you could move on to tier 2. And for regulatory purposes, tier 1 may be sufficient for supporting a grouping application for many of the nanoforms within the group. But again, if there's insufficient certainty in the data or too much variability, you can move on to tier 2 or tier 3 methods. So once you've completed the data acquisition via your IATA. So this would be data from existing sources, from computational or in silico methods, or via laboratory-based testing. Then you can populate your data matrix, and this allows you to assess whether your source materials and your target materials are similar to each other or not, and therefore whether they can be grouped. So to do this, really, you need some methods to assess similarity. So how similar is your source to the different nanoforms in the potential group? And so we've generated a series of new algorithms and used existing algorithms to assess similarity. And these fall into two types of algorithm. There are multidimensional methods where you compare all things measured, all endpoints such as deposition, size, surface reactivity for all of your candidates all in one analysis and assess similarity. Or you conduct them for one property at a time in a pairwise way. So you compare one nanomaterial with another in a pairwise manner. And Nina and Vendel will describe those methods to you later. We also need to make sure we can access existing data wherever possible. So the Gracious database links to, the Gracious framework links to databases such as eNanoMapper to allow you to access that data. And we've provided some new templates, not just for hazard data generation and capture, but also for physical chemical characteristic data and for release and exposure data. And this release exposure data has actually allowed us to generate a release exposure library of data from the project. And these templates are also available and have been published for other projects to use. We've also, as I said, we link the framework to the database, and I'll talk more about that in a moment. But we also need to make sure that the data is of good quality. And so we've also generated methods for assessing the completeness and the quality of the data that uses a traffic light system. And this is linked in now to eNanoMapper, so that when you look at the data within eNanoMapper, you can use this traffic light system to allow you to assess whether the data is suitable for grouping. So the framework is available in a number of formats. We've made it as a software blueprint. This software blueprint is open access. It will be published via Zenodo, so an open access repository. And it's available as a blueprint that can be incorporated into other software. So if other people are making risk assessment software, they can add grouping and read across functionality to that existing or new software by using this open access blueprint. So this open access blueprint is already incorporated into the Sun decision support system, and parts of it are being incorporated into the Guide Nano tool, and we will make it available to other software developers as well. We've tested the blueprint via a testing platform online, and this has been extensively tested by partners and by some externals as well. And Ralph will present this to you in his presentation shortly. We also have generated a guidance document, a full guidance document with all the details to allow you to progress through the framework in a stepwise manner. This is very detailed, about 120 pages in total. We realize that's too much detail for many people, and so we've also made a 10-page guidance in a nutshell version as an introduction to the framework as well, and Fiona will present that in a moment. We have allowed external organizations to use the framework to conduct case studies, and these have been conducted via universities and European research projects, also by consultants providing services to industry with relation to risk assessment, and also with regulators and policymakers within Europe and in the US as well. So the framework's been extensively tested, and we've used the feedback from this to improve the framework functionality. So you can see we now have our framework with the hypotheses, the IATAs. We have a blueprint for the software that incorporates all of these different components. We have similarity methodology, quality criteria, and a blueprint available for external organizations to incorporate the Gracious framework into their existing risk assessment software. We have case studies conducted, and we now have the guidance document available. So in terms of impacts, we've now provided clear guidance to support industry to conduct grouping and read across, both in a qualitative and a quantitative manner. We have a machine readable open access software blueprint, which I'm sure Ralph will describe in more detail later, to allow people to give grouping and read across functionality to software. And we have a framework that's understood and used by government bodies in the US and EU. We have a framework that's tested by industry, and we have a framework that can be used not just for regulatory applications, but also for safety by design and precautionary measure application. The framework is going to feed into a working party on manufactured nanomaterials at the OECD, which will focus on grouping and read across, and I will lead that along with the USA. And it's also being discussed by one of the PEG groups at ECHA. In terms of the framework, we're not just looking to exploit the whole framework, but also its individual components as well. The IATAs are easily edited to make risk assessment IATAs, and this is being done in conjunction with the BioREMA project. The tiered testing strategies can be used as standalone tiered testing strategies for particular hazard endpoints. The similarity methodologies are being incorporated into read across capabilities of Guide Nano tool. The templates we've generated for data acquisition can be used by future projects. We have the quality and completeness score methodology, which is not just relevant to grouping, but risk assessment in general. And we've also generated a wiki, which Alex will describe later on, to allow harmonization of terminology. So that's the end of my presentation today. I'd like to thank you for listening, and I'll just check the chat to see if there are any questions. So thank you, Elisa, for providing the information on the materials that you're interested in. So I will use that as an opportunity to switch to another presentation for you. So I have generated a series of slides which go through the different hypotheses and the different IATAs, and I'm going to share this with you now, and I'm going to link it to the materials that are described in the chat. So okay, so Elisa has said that she's interested in silver nanowires and graphene nanoplates. She's interested in zinc oxide and high aspect ratio nanomaterials and multi-component nanomaterials. She's interested in human health, the inhalation route, and she's also interested in the environmental water compartment. So I'll focus on the high aspect ratio nanomaterials and the silver nanowires. So if I just look at my presentation, so you can see here I have lots of slides with different hypotheses for different routes of exposure. So here are my oral ones, here are my inhalation ones, and here's my first. If I just show you this, these are the list of hypotheses for the inhalation route of exposure. So you can see we have a couple of hypotheses that relate to high aspect ratio nanomaterials. We have hypotheses that relate to instantaneous dissolution, quick dissolution, gradual dissolution, and very slow dissolution. So shape and dissolution rate were key physical and chemical characteristics that were found to help in the development of hypotheses. So if we look at the high aspect ratio nanomaterial hypotheses, the first one states that following inhalation, exposure and long-term pulmonary retention of high aspect ratio nanomaterials can occur, resulting in lung toxicity. The second hypothesis, excuse me a second, just get my laser pointer. So the second hypothesis refers again to high aspect ratio nanomaterials, and this time refers to the potential for these to translocate to the pleura and cause mesothelioma development. So this is how the IATA is structured. So the hypothesis is quoted at the top, and then we have these decision nodes in blue going from top to bottom. So the basic information stage allows us to identify that inhalation is an expected exposure route. And the basic information also allows us to identify that this is a high aspect ratio nanomaterial. So the first question is, can the high aspect ratio nanomaterial deposit in the distal lung? And there will be a tiered testing strategy behind with the methods required to allow you to answer this question. So if the answer is no, then you're going to deposit in the upper airways and be efficiently able to clear this material from the respiratory system, and so the hypothesis is rejected. And in fact, there is a suggestion you could consider the oral route of exposure instead. If the high aspect ratio nanomaterial can deposit in the distal lung, then the answer is yes. And so the next question is about the dissolution rate. So does the HARN dissolve very slowly in lung lining fluid? So does it have a half-life of more than 60 days? This question is important because it tells you about the biopersistence of the high aspect ratio nanomaterials. So if it has a half-life of less than 60 days, the answer is no, and you would reject the hypothesis, and it gives you suggestions of other hypotheses to consider. Instead, if the answer is yes, the half-life is greater than 60 days, then you move on to consider dissolution inside the cells. So inside the cells, particles can be exposed to pHs as low as 4.5 in the lysosomal compartment. So again, if the half-life is greater than 60 days, the answer would be yes. And you would go on to assess whether the fiber length is greater than 5 micrometers. If the answer is no, then these particles can easily be cleared by immune cells from the body, so you would reject the hypothesis. But if the length is greater than 5 micrometers, they're not cleared by immune cells. And so you would then go on to the next question, which assesses the rigidity and whether they maintain a needle-like morphology. Because if the fiber can be folded up inside a macrophage, it can be cleared. And if it's rigid, it can't be folded. And so your answer is yes. Then you would assess the potential to cause something known as frustrated phagocytosis, which is an inability of immune cells to take up the fiber. If your answer is yes, then you know that you can potentially group your high aspect ratio nanomaterial as biopersistent, rigid, and able to cause lung hazard. At this point, then, you can assess the hazard in more detail by looking at the inflammatory response, and this allows you to then decide whether you want to conduct read across between your nanomaterials within your group, or whether you need to consider other applications. So that gives you an idea of how you would use some of the information there. I'm just going to have another quick look at the chat. 3 minutes. Thank you, Stella. Okay, so I think I'm going to stop there. That gives you an idea of how we can apply the grouping framework to an example provided by one of the people on the call today. So thank you, Elisa, for that. And I'm trying to stop my show. There we go. Stop sharing. Okay, thank you. I think it's now time for me to pass over to Ralph. Ralph, just checking you're on the call and you'd like to share your screen.
Yes, I would like to share my screen. Good afternoon, Vicky.
Thank you.
Let me try to find the share button.
Okay, so while Ralph is putting his presentation up, so Ralph is going to introduce you to the blueprint testing environment that we have used to assess the framework and how well it works. So thanks, Ralph.
Yeah, afternoon, everyone. My name is Ralph van Houten from ThinkWorks, and ThinkWorks was the partner responsible within the project for the development of the Gracious blueprint. The blueprint was already briefly introduced by Vicky as part of the overall concept of the framework. I'm going to present a few slides to position the blueprint within the project and what it is about and for who is it intended for. And then I'm going to switch to the online demo to give you a bit of an impression how the framework could operate in a software environment. So what is the blueprint about? Vicky already briefly introduced it, but what we try to do within the project is, at the left, you can see all the content developed within the project. So the IATAs, the decision notes, the testing strategies, the overall framework itself, similarity algorithms, etc. So that content, we try to model that into an object-oriented model. And that object-oriented model is something which is suited for software developers to easily understand and to also make tailored implementations or derive tailored implementations in different systems. So this object-oriented model was designed in an environment which also helped us to automatically generate a PDF, so basically a big textual document containing almost around 375 pages with all the content modeled in this object-oriented tool. That PDF document is the base and is also the main deliverable of our task. And that can then be used by other software developers like Sun already did. It's a decision support system to, for instance, implement the IATAs of the blueprint in their environment. We also are going to implement parts of it in the Guide Nano tool. And of course, because it's publicly available later on, other tool developers can use parts of it or the entire thing to develop own software or integrate it in their products. Besides the PDF document, also a JSON format is made available. That's a more machine-readable format, actually of the same object-oriented model. And that format can then, for instance, be used and is already used by eNanoMapper to map data and endpoints from that onto the gracious endpoint descriptors in the framework, but also can be used by other services. And also later in the day, there will be a session on the Gracious Wiki, which also relies on this JSON input as a way to represent the data there. This development was done in an iterative way, so it helped us to get feedback from the experts on the one hand in the project via the object-oriented model and the wiki to get more specific definitions and to improve them. But also we developed an online blueprint test environment, which is basically a layer, a graphic user interface on top of this model to check what we were actually modeling results in software, in good runnable software, and also that allowed us to test cases and provide feedback to the partners in the project, which then could improve their IATA or restructure the IATA. And that was then yet again incorporated into the object-oriented model. So it was an iterative approach which we used. And that finally led to the blueprint as we have that now. Let me just give you a brief impression about the content. If you are more interested in the development of the blueprint and the test environment, there are 2 movies available. You can access them via the website. And then I'm going to show you a bit of give you a bit of an impression how the content of the blueprint is organized and what you can expect there to be in there. So one of the things already shown by Vicky was a class diagram. Many of class diagrams are in the PDF, and they are basically describing the basic key elements to be used for implementation, the relationships between them, the attributes attached to them, etc. So this is for software developers a known way how to describe these structures and also to use them for implementation. Besides these kind of class diagrams extracted from the framework, also the blueprint contains the decision tables. And these decision tables describe the flows in the different IATAs, but also the tier testing strategies per decision node. And there are hundreds of these decision tables in that PDF. So there's a lot of content already in there. Finally, an important part of the blueprint is about the good description of endpoints, assay, cell types, medias, etc., used throughout the framework. So it contains a lot of descriptors and also the definitions attached to that. And later this afternoon, the wiki will be shown, and this also is presented there. So this is just to give you a glimpse of what the blueprint document contains. But of course, it's also relevant to see how the total framework could operate in a software environment. And therefore, I'm going to show you now and to demonstrate the test environment. So I have to switch to the application and to give you an idea how the framework actually works in a software-like manner. So if everything goes well, you can see the intro screen with the Blueprint 0.9 version. You can imagine that an end user normally gets an online account to a software tool and then can log in there. So I have to do that also. And then the user can start working on a case or add a new case or work in an existing case. I prepare the case because of time efficiency. So I just click on this. And this case is an internal case study which has been worked on with the integration project and enriched with some parts I added to make sure that all the functionalities are addressed in this case. So when you start, you can see here this this overview of the workflow. So basically, as you can remember, Vicky introduced a flow of the framework. So you start off with identification of what is the candidate nanoform you want to group or read across, or the set of candidates, and also to allow you to indicate what the purpose of the assessment is. Let's do that first. So when you click on the purpose, you can indicate I'm interested in a more precautionary assessment or safe by design, or I wanted to assess it from a regulatory perspective. I chose here regulatory, but the user can switch. When we go back to the workflow, the first step after the purpose for grouping is, of course, to introduce the nano form or the candidate nanoforms. And you can do that just by clicking here. Then you have the option to add a number of candidate nanoforms. And here, the candidate nanoform shows here are all carbon nanotubes, I think 15 in total. And the information there is provided by one of the case studies in the project. When we go back to the overview, the next step is to provide basic information for these candidate nanoforms, like the chemical composition, the morphology, the shape, etc. So we can go and click on here. And as you can see, for each of these candidate nanoforms, we have the option to provide the basic information. That can be the appearance, the composition, like what are the main constituents, what are the surface treatments, etc. What kind of classifications, CLP classifications are available, what's crystallinity, that kind of information can already be provided. The shape, like what category it is it elongated, is it spheroidal, platelets, or is it a combination of those? What is the aspect ratio? And as you can see, the tool also allows to indicate whether the provided information is an estimated value or it is based on actual measured data. And you can do that for each property in the user provides. You can provide information on the size distribution for the smallest size, for the largest dimension, and you can do that for different percentiles. So you can build up a size distribution. You can provide information on surface area. And this is all more in a tailored way, but you can also provide any other kind of property in a generic way. That can be done here, the properties and endpoints. So if you have, for instance, values coming from literature studies you want to use, or provided by a supplier or whatever, this part allows you to introduce any property which the framework is known of, and that are literally hundreds. And you can see here, you can enter the information per property, also the ones which are not considered basic information. Here you can see how you can do that. For instance, first you add a new property. You select the category to which a certain endpoint or property belongs. These are organized according to the way the OECD harmonized templates are organized. For instance, if I select here one human health cytotoxicity category, then once I've selected that, I can go to the actual data endpoints to be selected. So that's basically the one for which you really provide the information. You can do that for individual properties, but often the data is provided as an entire assay. So you also can provide the data per assay. So for PhysChem, you can say, okay, I want to provide data coming from a vortex shaker or dot shape analysis. We have assays for the environmental assays, so for biodegradation, etc. All of these are described within the Gracious framework or used in one of the tier testing strategies. Also on the eco hazards for the toxicity of the of eco compartments, or human health hazard assays and related assays. So you can see there's a lot of information here. Vicky also introduced the fact that we allow the user to use existing data from the Nanomapper database. So I also want to show you briefly how that's done. You can select a nanoform and then can browse through the Nanomapper available source data. You can click on it and then it's automatically loading the data. In this case, for this top YAC material, you see that 68 different assays were loaded for PhysChem, eco, and also human hazard. And then you can look at each of these individual assays which have been loaded and see the values in there, and also have a graphical overview of the data points in it. So there are several ways of providing data individually via a tailored interface or even via the database. When we go back to the case, we see that besides the information on the candidate nanoforms and source materials, etc., we also can provide information on the use of the candidate nanoforms in the context of an application. And the application is often a nano-enabled material or nano-enabled product or article. So if you want to provide information on that, the test environment also allows that. So if I click on here, this part of the test environment allows you to describe nano-enabled products, but also, of course, the candidate can be a product on its own. It can be a powder form and then supplied to another factory who's going to use it to incorporate it in their product. For instance, as an example, we made a polymer, and that polymer will be enriched with the candidate nanoforms, for instance, to strengthen the matrix of that polymer. So you can describe here this nano-enabled product. And then the next step, of course, after you've introduced these nano-enabled products, you can introduce the way they are used in the life cycle. So you can go to the life cycle and start adding use descriptions. I already introduced one. So in this case, this is about embedding the carbon nanotubes into the polymer. So that's that use. And within that use, you have certain contributing activities. So you can describe individual contributing activities within that use. You can also indicate what life cycle stage you're on, what the sector of use is, what actually the part of the nano-enabled product is you are considering within this activity, and what the corresponding exposure scenario is. So all that information can be provided. Each use scenario must at least have a contributing scenario. So you can indicate, for instance, here that before you can mix it, you have to fill the drum or whatever kind of process you use to allow the mixing. That can be done from different perspectives, like an occupational exposure perspective, but also an environmental one. So you can add as many activities, contributing activities as required to describe your use scenario. You can then indicate a specific activity, what kind of level of energy is involved, etc. So all that information together with the information provided on the nanoform is then the basis for triggering the appropriate IATA. So let me go back to the overview. So now what we have done is we have indicated our candidates, the purpose, the candidate nanoforms. We have provided the basic information for that. We have described the use and introduced the nano-enabled products where these candidates might be incorporated in. And now we get to the next step, and that is the actual assessment. Okay. So when we go to the grouping scenarios menu here at the top, you can already, I prepared one here that's basically linked to the contributing activity, and it's about filling the mixer with the carbon nanotubes. And here you can see all the candidates listed. So we are going to do the same exercise for each of the individual carbon nanotubes in our set. So we have like this. But we could also say, let's directly go and try to do an environmental scenario without the use, and just assume that the release is there or the exposure is there. So I can click on this, and then I can say, okay, what happens when we pour these carbon nanotubes, for instance, in a wastewater treatment plant? You see, then that then immediately creates the candidate nanoforms again and triggers a certain environmental IATA. Okay, let's just remove this one. And let's go back to our inhalation one. As you can see here at the left, these are at the moment the triggered, the relevant IATAs. And the first ones here at the top, those are the ones related to exposure and release. What you can also see is in the beginning that indication of positive, missing, not yet implemented, or negative. And basically that's the outcome of an individual IATA. And how that works is that each IATA has decision nodes within it and is used then to, and these decision nodes can then lead to an outcome for that IATA. And that as a consequence might trigger other IATAs become relevant. So in this case, this first we look at, is release possible? Yes. Then that triggers the second one, is then as a consequence of that also exposure likely? And that's the case, yes. And that then triggers the inhalation IATA Vicky already shown. So that these are the HARN IATAs, the first two, and then the dissolution related IATAs. And if you look at that, we can have a look at how an individual decision node is organized. So this pane here, this top one is in the green, is an where they go decision node. And it's the same question Vicky already showed in her example. Can HARNs deposit in the distal region of the lung? And attached to this decision node is a decision table with the rules how to derive from provided data an outcome for that decision node. And some decision nodes have that capability, and others rely more on expert judgment because the rules are not always easy to implement or implementable. As you can also see, is that the tool at a certain tier level provides information on what are the assays to be best used to provide the required information. So you can see here at tier level 1, we require some information on the smallest dimension and the density in order to derive the aerodynamic diameter. And these are assays which can provide data. So the tool helps the user in guiding towards the most appropriate assays. Also, you can see at the bottom that the tool also provides information on whether it's required or whether it's relevant to tier up, to escalate to the next tier. So if you have to change this tier 1 into a tier level 2. And if I click on this, you will immediately see that the tool indicates different data requirements to answer the same question at tier level 2. And you can also go to tier level 3. So that's more the in vivo related properties there. So let's go back to the first tier level. So if you have an answer for this decision node, then as shown also by Vicky, automatically the next decision nodes become relevant. And you can do this by expert judgment, but you can also rely on the data. That depends on the decision node. And as you can see here, we can indicate whether the candidate nanoform dissolves quickly in the lysosomal fluid, what is the length of the horn, etc. If you do that for all the candidates, then at the end you will see that, let me go to the horn IATA, just to give you an example. At the end of the IATA, you can see whether this IATA comes to a conclusion. So in this case, because the horns are no longer than, the length is no longer than 5 microns, this IATA is not considered positive, and macrophage uptake is likely to happen. And it also indicates that you can also have a look at the inhalation IATA for slowly dissolving non-fibrous nanoforms. And as you can see, that's this bottom one. This one is positive. And here you can see the first node is where they go decision node. And then here you can see data decision nodes, which actually try to gather the data for what they do in the cell or in the body. And you can see that this is data requirement on the reactivity and on the information. And then, of course, when you have done this for all the candidate nanoforms, you can create data matrices. And I also have an option here which I can try to share you. I hope I can bring it on screen like this. So make it a bit smaller. So what you can see here is that we can generate a similarity matrix based on for all the candidate nanoforms. And the first one, in this case, is the one we compare the other candidates with. And we do that property by property. So each cell is a similarity comparison between the one candidate and the other ones per property. So these ones are for the basic information. And you can see here the similarity property by property for the endpoints and the properties at tier level 1. And as you can see from the coloring scheme, this is an n-fold comparison, and you can already see that this first one is most likely not to be grouped with the second one and the fifth one. So this already gives you a clue or an indication which of the candidates could be grouped or not. And you can also add source materials to this list of candidates and to see whether or not a read across between your candidate and another candidate might be possible if that's a more data rich one. So this is basically, well, everything what you've entered from an information perspective and in the IATA ends up in a decision, a data matrix per IATA. This will, of course, be further discussed in the session on the similarity later on this afternoon. And yeah, this is basically to give you an impression about what the blueprint offers and how software could implement the Gracious framework. And I would like to thank you all for your attention. It might be that there are questions.
Thank you, Ralph. That was excellent. There was one question from Amar in the chat, which was about the possibility to add new hypotheses to the framework in future after the Gracious project has been completed. And so I replied to say to him that some of the new NMBP 16 projects, such as Sunshine, Diagonal and Harmless, are actually looking potentially to either use the existing hypotheses, adapt them, or make new hypotheses, and they will be able to feed this into the existing framework. And maybe, Ralph, you could say a little bit more about some of the NMBP 15 projects, and if there is any opportunity via those projects to feed in those kinds of changes or additions.
Yes, basically what we try to do with the blueprint is, of course, also use them in those projects. We know the blueprint will be used in the Sabina project for one, and also in the Safe by Design for Nano. But then we are focusing on different parts of the blueprint. So as you already mentioned, one project will more focus on using similarity for read across, as the other project will focus more on using the descriptor framework behind it to map and exchange the information of endpoints. And as you already mentioned, if in other projects new IATA are developed, the blueprint framework is already prepared for that, as you can see here in this not yet implemented indication. We can just add a new IATA class to the blueprint, and that it's automatically incorporated into the framework. So it's flexible in that perspective. It's not fixed to the existing predefined ones. So we can add new ones in future.
Thanks, Ralph. And Amar will also be looking at this framework in the OECD. So I don't know if the OECD working group might also consider adding in new hypotheses and IATAs. And of course, we're not sure yet what ECHA will do with respect to the framework, whether they will just refer to it or what. We'll have to wait and see on that. There might be options there as well. Okay, thank you, Ralph. Our next presentation is by Fiona. Ralph, could you stop sharing? That's great, thank you. So Fiona, I think you can share your screen now.
Hello, thanks, Vicky. I'm just getting my slides up onto the screen now.
That's great, we can see them perfectly. Thank you, Fiona.
Okay, great, thank you. So my name is Fiona Murphy and I'm from Heriot-Watt University. And today I'm just going to very briefly introduce you to the Gracious Framework guidance documents and what these documents include. And I'm really presenting this on behalf of Neil Hunt from Eurodis, who put a lot of work and effort into getting the guidance documents together, but unfortunately can't be with us at the workshop today. So as Vicky mentioned in the introduction, we actually have two documents available covering the Gracious Framework. So the first one, we consider the full guidance document. And this is aimed at technically competent people who are familiar with grouping concepts and read across and have a basic understanding of the overall goals of the Gracious Framework. It's quite long, so it's over 100 pages long, but it really provides a full outline of the complete process of using the Gracious Framework, which a user can then apply to their particular grouping question. And then on the other hand, the second document that we have is our guidance in a nutshell. And this is more of a short summary document aimed at someone who's completely new to the Gracious Framework and who's looking to understand the basic concepts and get a general feel for how the Gracious Framework would work. This will allow them then in the first instance to consider whether grouping or the framework itself may actually be suitable for their needs. And from there, they might progress to further discussions about how they would apply it or if they would want to use it. So within the full guidance document, each section covers a separate part of the framework, starting with an introduction to grouping and an overview of how the framework itself works. Then move on to the basic information step, and this point allows the user to define their candidate panel of nanoforms, their purpose for grouping, and the potential context or exposure scenarios that they're interested in. We then move on to the more detailed information step, which goes through the process of how you would select one of the predefined Gracious hypotheses and IATAs that you to test that may be applicable to your panel of candidate nanoforms, and then how to conduct a similarity assessment within this context. This is then followed by guidance on how to use the output from the grouping that you've conducted by using the framework. So for example, how you might progress to read across if that was of interest to you. We then also within the guidance documents have descriptions of the tools that support the framework that are available, such as more details on the blueprint, which Ralph has just described, or the wiki. And finally, the final section is how to write your own grouping hypothesis and some guidance on that if none of the greatest predefined hypotheses that we've already described apply to your test case. So each of these sections within the guidance document follows the same format, which includes an introduction, instructions to the users, and also details of a worked example. And this worked example is used to illustrate how instructions for using the framework have been applied in a real test case example. The worked examples were generally selected to illustrate or highlight specific points of the framework which may require some user interpretation. And this is to try and avoid or to minimize any ambiguity in using the framework. They therefore actually differ from the case studies, which if you're coming to the workshop tomorrow, you'll hear more about, which were selected to actually test the performance of the IATA and the overall utility and usability of the framework. Within the guidance document, there's also a section on how to find out more. So if there's any further reading or resources that are considered appropriate for each section or applicable to each section. And then we also have provided some additional tips for new users in boxes throughout the text for each section of the guidance document as well. And these provide some extra information which may not be familiar to all users who are trying to use the framework, or they may clarify some points which may help a new user to apply the framework and correctly interpret the results. They also may provide some additional definitions which may be unfamiliar to new users, or some tips and hints included to generally expand the user's knowledge around an area to aid interpretation. So on the other hand, the guidance in a nutshell document is much more of an introductory document for completely new users. It's written to be hopefully more accessible than the full version. It's much shorter, it's only about 10 pages long. So all it really covers is it gives you a brief introduction to each section of the full guidance document and provides a list of the instructions that are covered in each section rather than going into detail. So the aim is really more to introduce the concepts and structure of the framework, but we would not consider it sufficient in isolation to really conduct a grouping exercise. So it can be more considered a starting point for someone who is unsure about whether the framework or grouping is actually suitable for their needs, and allow them to make that judgment before going into the detail of the full guidance document. So if you want to try and find these documents to read them and to find out some more, both of them should be available on the Gracious website, and they're also soon to be uploaded onto the open access repository Zenodo. So I just want to finish with these are some acknowledgements from Neil, who really wants to thank some of the other partners who are involved in both writing and reviewing of the guidance documents, and especially to Vicky and Eric, who provided a very comprehensive review of the final versions, but also to the full Gracious team who were involved. So thank you if you have any questions.
Thank you, Fiona. That was great. That was really clear. I don't think there are any specific questions for Fiona on the guidance document. There was a question about when the guidance document will be available. So there's already a near final draft version on the Gracious website, and Stella has posted a link to that. And then Fiona has indicated that the final version will be published hopefully later this month on the Zenodo website. It literally is a couple of typos and a couple of references to sort out, and the formatting to make it look more professional, and it's complete. So that's great. Thank you, Fiona.
Yeah, thank you.
Okay. I think we're in a position now to move on to the next session for this afternoon, which is the Gracious Similarity Assessment methodology. And the first presentation is by Wendell, and that's going to be on Introduction to Similarity Assessment. Thank you, Wendell.
Okay, hello everyone. Let me share my screen. Are you seeing the right screen, which means the full screen?
Yes, yes, thank you.
Perfect. So it's my pleasure to introduce you to the topic. And I have to stress that this was a work by many partners. Certainly something like 30 experts from the Gracious Consortium have contributed to the development of similarity tools. Why do we need it? Well, first of all, it's repeatedly mentioned in the ECHA guidance, but they don't tell us exactly which algorithm to use. They don't tell us how to assess similarity. They did tell us that we need to look at similarity. I just highlighted a few instances in the guidance. And they also pointed to the logic that we should seek for similarities in phys-chem properties, etc., mainly using phys-chem parameters and or in vitro screening methods, which is exactly what the tier 1 and tier 2 methods of the Gracious IADAs do. They are phys-chem and in vitro methods. And so we wanted to clearly position this assessment in our framework. You have seen this slide from Vicky, of course. And the point is that once you have a data matrix, then you need to assess that data matrix. And Ralph has shown that one of the algorithms is already directly included in the blueprint. And he's shown you a data matrix that had green, orange, and red highlights, which were already the result of a similarity analysis. And in the terminology of ECHA, this is step number 5. So once you have a data matrix, you need to assess it, and you may have sufficient evidence to justify grouping. That's fine. Then you're done. You may not be just satisfied, which means you can escalate it to a higher tier of testing, and then the whole cycle is being repeated. This is this cycle here in the ECHA diagram. We have generated a white paper that is currently under peer review to describe methods, both existing and novel methods, to assess that data matrix. We do focus on a pairwise comparison of nanoforms in 2 ways. We call it property by property, which means that we compare the similarity in reactivity, and independently of that, we compare the reactivity in, let's say, loss of organic coatings. And then you need to analyze both of them independently. Or you might do a multidimensional analysis, such as dendrites, which will be also shown in a second. It is very important to keep the terminology clear, and that's also part of the white paper. When we say property, we mean a basic phys-chem parameter or a descriptor of the aspect of the nanoform interaction with the immediate surroundings, which could be the property of reactivity, property of attachment efficiency, etc. A descriptor then means a single scalar number accompanied by units. So for instance, the D50 size median is a descriptor for particle size, although what you have measured initially is probably a particle size distribution. Likewise for the Lowell in terms of a dose response and toxicity. Please keep in mind the data matrix should contain all and only the descriptors required by the specific IADA for the specific hazard. It's not about an assessment of everything you know about the 2 nanoforms. It's about an assessment of what counts, what matters. And this is exactly what Vicky has presented. The IADAs follow a logic. They are based on science, and they identify only the relevant decision nodes. And this is what we assess here. The list of algorithms is of course not complete here, but these are the ones that we have been looking at. And I will leave the details to the white paper later on, just to mention that some of these algorithms have been used before. Euclidean distance is extremely popular. Many people use different versions of cluster analysis. The X-fold difference is also used in the Asetok Nano app for registration of nanoforms, which is a different aspect of nanoform comparison. But also some more novel algorithms are really interesting, and we'll see results in a second. We look at pros and cons, and we now test them. We first test what is maybe more popular. We have seen many papers using clustering approaches, which are measures of a multidimensional distance. Let's look at an example here. And I'm sorry for the busy slide, but now we're really getting into the details of what grouping and similarity analysis means. Let's look at the top diagram here. Let me get the laser pointer. And let me try and mute my phone. I'm sorry for that. A pairwise comparison means that we compare here the barium sulfate NM220 against itself and against all of the other materials. And in this specific case, red means very different and green means very similar. And obviously, each material is very similar to itself. But here, the overall comparison between the barium sulfate NM220 to zinc oxide NM110 is very different. So far, so good. This is what we would expect. A rather reactive, dissolving material such as zinc oxide is really different from a not so reactive, not really dissolving material like barium sulfate. But these other two highlighted cases here are a bit more complicated to understand. The zinc oxide compared to the titania has a score or a distance of 3.1, which is round about the same as the comparison of these two forms of iron oxide. When you now look into the individual decision nodes that constitute the overall comparison, and that is, as you see here, the dustiness, the dissolution under lysosomal conditions, the cytotoxicity by an in vitro test, and the reactivity by an abiotic test. These are the four decision nodes in our inhalation IATA for particles, not for fibers. Then you see that the case of zinc oxide to titania here is dominated by the difference in dissolution. And the case of the two iron oxides here is actually quite different in most of these properties, except for their dustiness behavior. So when you compare these two cases, the distance is roundabout comparable, but the actual difference of biological behavior is not comparable at all. So this is a challenge for the multidimensional differences. They may suggest a similarity that is not actually a biological similarity. It is also interesting to look at dendrograms. And what we did is we used one and the same data matrix, and we used different metrics of the multidimensional distance. This is work from Nina, who's also going to present examples in a second. The same data matrix analyzed by different algorithms. Let's look at the dendrogram that compares materials here. For one distance metric, the relation of these two iron oxide materials down here is quite different from their relation in the other dendrogram here, because here they are seen as relatively different from, for instance, barium sulfate, which is up here, but here they are all in the same branch, still with a difference, but in the same branch, separated from the others. Also, when you compare the vertical dendrogram here that looks at correlations between properties, it's interesting to see that size is suggested to be somehow related to dissolution rate, whereas here it's more somehow related to reactivity, and dissolution rate is in a completely different branch. So we are not so sure if the suggested cause and effect conclusions are really robust in these approaches. It is still interesting to use these multidimensional approaches, but we think they are more a tool of discovery for scientific purposes, less a tool for regulatory purposes, where instead we would recommend to use property by property evaluations. And we'll come to that now. Using the same data matrix again, and we just look at one property, in that case on dissolution. We just look at one algorithm here. In that case, the ordered weighted average or Arcusinus-based similarity from Alex Sabeo. You see that we have red colors for any comparison to zinc oxide and orange colors for most comparisons to barium sulfate. This is because the zinc oxide dissolves quickly, barium sulfate dissolves partially, and all of the other materials that we are looking at here dissolve very slowly. So far, so good. This seems to be reasonable. So we expect this orange and red color for these two materials. The serum dioxide compared to itself, iron oxide compared to itself or to their related nanoforms, all come out as quite similar. Now we compare the same plot by different algorithms. The X-fold approach, the Bayesian factor similarity, the half-time Euclidean distance as absolute difference, and the ordered weighted average based similarity. As you can see, the three pairs A, B, and C are comparable, but we have quite different colorings, so different assessment of similarity for the Euclidean absolute difference. That can be changed when we now perform a data transformation, Yeo-Johnson data transformation, before performing the Euclidean distance. And that's important. The data transformation is part of the process. It's absolutely justified to perform it, and we need to perform it. Otherwise, we have inconsistencies between the different algorithms. On a specific example, when these are dissolution kinetics, and that's actually the measured dissolution kinetics in different fluids for different silica forms, never mind about which material it's which. This complex behavior here is condensed by fitting half-times, right? We do this since decades. Now, the half-time can now be compared one to another. And here, the interesting point is that in one simulation fluid, under neutral conditions, extracellular fluids, we get the upper part of the diagram here, where, as you can see, we have lots of red colors. So especially the aluminum doped materials are not similar to the others. Whereas in a different fluid, under lysosomal conditions, all of the silica-based materials, which are colloidal silica, are similar to each other, but different from the red color, the precipitated NM200 silica. In fact, this behavior, especially with the two fluids that we need to look at here for silica, is confirmed by in vivo findings. And that brings us to the question of what is an acceptable similarity and how does all this relate to in vivo behavior? In this case, we have the in vivo data and we can confirm that indeed the similarity that is suggested for all materials except the aluminum modified materials is confirmed. In another example, let's look at attachment efficiency, and this is work from the Nanophase project. The dynamic range of a descriptor is important. The attachment efficiency has a very wide dynamic range. It can take reasonable values from 10 to the minus 10 to 1. But by performing the model, in that case, the model from Nanophase, we see that only for values between 10 to the minus 4 to 1, the transport behavior is actually changed by that property. So this is the environmentally relevant range. We now can explore to which extent a 10-fold change around something like a median would impact the transport behavior. And it is that range that we use as the floating band of acceptable similarity, because even for a 10-fold difference, we have only a minor modulation of the total transport behavior, which has consequences for our measurement, because if we want to assess materials against a 10-fold group range, we need something like a 2-fold accuracy to have a good judgment whether a material is still within or outside of the group. 2-fold is still challenging for many methods, especially for those that look at interactions of nanomaterials with their surrounding environment. I'm not going to present now the calibration strategy, but in the case studies tomorrow, you will have many examples where we want to demonstrate how we follow that tiered approach to reduce animal testing. The tier 1 is based on phys-chem or in vitro methods as suggested by the guidance. And so it must be conservative, right? We may need to make sure that we don't falsely group materials. It needs to be calibrated like any alternative technique that prevents, replaces, reduces animal testing. It needs to be calibrated. This is what we do by having case studies where we have both the tier 3, very reliable in vivo data, and we compare our tier 1, tier 2 alternative methods. But during the use of the framework for future users, it would mean that having made tier 1, you might get a rejection of some candidate nanoforms. You have the option, like Ralph also presented it in the blueprint, you have the option to escalate to higher tier testing. And maybe that helps you to still justify the grouping of nanoforms, or maybe it puts an end to it. Let me summarize here. The testing of algorithms for the assessment of data matrices has led us to conclude that the data matrix needs to include representative test materials, which represent the biologically relevant range, which also means that whenever we perform a similarity assessment, we actually perform it on at least 3 substances: the 2 representative test materials, which span the relevant or biologically relevant range, and the substance in several nanoforms of our case study. We perform that assessment pairwise and property by property, and we found good consistency for the X-fold, Bayesian, and OWA distance algorithms. And it also works for the Euclidean distance with proper data transformation, Yeo Johnson in that case. To give you an estimate, in our examples, we find that the similarity score, or I guess Nina should say, I should say distance, for the pair of representative test materials, which means the distance from your positive to your negative control, is typically around 100-fold. And that is clearly non-acceptable because these are the 2 opposite cases. We often find, and just call it the rule of thumb because we need more evidence on that and follow-up projects, but we often find that for relevant properties for where they go or what they do, similarity scores between 2-fold and 5-fold are that range that's interesting because it's metrologically significant, but still biologically acceptable. Talking of follow-up, we will look at the qualitative similarity of form of release here for more complex materials. Talking about advanced materials, we often have non-nano components, so this is interesting to consider. We will also have to look at that, and we may have to look at mixtures. All this is beyond scope of Gracious. It's not only harmless, it's also Sunshine and Diagonal that will look at this. So this is the future. Thank you. I think we should go directly to Nina before we go to any questions.
Well, Vandal, there is one question which I think you can quickly address, and that's from Elisa again, which is, are the algorithms considering the relationships between different phys-chem properties, for example, size and shape effects on dissolution, depending on the curvature of the surface?
Yeah, good question. We can use those algorithms for the phys-chem properties. We also use them for in vitro properties. The algorithm itself is not specific to any property or method. We assess anything that is in the IADA. If the IADA says we should look at dissolution, we look at dissolution. And you're right, of course, oftentimes dissolution or surface reactivity scale with the curvature radius or the specific area. But I think our IADAs made a good decision to focus on assessing directly, in your example, dissolution, and not trying to predict it from radius of curvature.
Thanks, Wendell. Nina says she's also going to address this in her talk. I think there's one thing that you and I didn't stress in our presentations today for the similarity assessment, and that's when we do it, the data needs to come from the same SOP, from the same method. So for example, if we're measuring, we're doing a similarity assessment for surface reactivity, it needs to be from the same assay. You can't mix data from the DCFH assay with the FRAS assay. So I think that was something we maybe didn't stress today, but it's important to say. Okay, thanks, Wendell. So well, it's time to hand over to Nina.
Do you see my screen?
Yeah, we can see you and we can hear you.
Okay, great. And you see the slides, right?
Yeah.
Okay. So, okay, I'm starting the presentation.
Thank you.
Oops. Oh, thank you, and thank you, Wendell, for the introduction of the similarity. I'm glad to present what. First, I was glad to be involved in all this work, and I will try to make all these algorithms a bit more user-friendly and not complex as they might seem. So first, you understand, and for similarity assessment, we need a data matrix. What I'm trying to show is the data matrix which have been compiled for the Gracious white paper, which is under peer review right now in Null Impact. And these properties which have been compiled according to the IATA hypothesis by experts. So this is we are following the rules. What I'm showing is actually a file you could, or file format you could use to upload your own data into into an online form and calculate the similarity. This is something new which not everybody has seen yet. Here we can also specify the biological relevant range we want to consider, and we understood from Wendell's presentation this is important. So we consider dissolution, dustiness, inflammation, reactivity, and eventually we can explore size and surface area. This is a quite new tool where you could upload your own file and generate similarity matrices, and this is the result you can get when uploading the file from the previous slide. I'm going to explain each of the figures in the next slides. Okay, so here is the similarity of dissolution, and we have descriptors. We have two descriptors for dissolution, which is half time and dissolution rate. And on the rows we have, and on the columns we have different distances. On the first column we have Euclidean distance straight with the data, and on the second column we have Euclidean distance with normalized and log transform data. And on the third column for reference we have X-fold. So this is once again an illustration that data transformation is important. And here I'm using log transformation instead of Yeo-Johnson, but which is easier to use. So this is an alternative if you would like to have easier calculation. On the third row, we have two-dimensional distance, but they are for the same property. So we're basically combining two descriptors for the same property. And I think this should be considered a nice way to apply to multidimensional distances. Oops, sorry, it seems like I have some recording, but okay, so I would like to show a bit of background because if we talk about Euclidean distance and we all know Euclidean geometry from school, and we know Pythagorean theorem, which is basically how you calculate Euclidean distance on a plane. And on a plane, if you consider the word flat, then the distance, two-dimensional distance between two cities is basically the length of the straight line between them. But of course, we have many other distances, the real distances, which might be not the straight line, but a different driving distance, for example, or the way the plane fly. Sorry, I'm sorry for this.
Nina, do you have some recordings on some of the slides? Is it causing a problem?
I shouldn't have it. Yeah. So yeah, yeah.
I can easily help you to get rid of it.
Yeah, if you could
okay,
mute
so,
it.
No, I can't. If you just escape from slideshow.
Oh, okay. Yes. Thanks.
And then go to slideshow at the top. Top in the middle. So top row, middle. Keep going left.
Yeah.
Slideshow. Hit
okay.
slideshow.
Yeah.
And then next to the clock, there's play narrations. So click that to turn it off.
Yes.
Yes.
Yeah.
Okay.
Yes. Okay.
There you go,
Super.
And then you go.
Thanks a lot. I should have checked this. Okay. So I'm really sorry, and thank you, Vicky, a million. This we're going back to mathematical description of distances, and we already know that Euclidean distance is straight distance between 2 points on a plane. We also have the so-called Minkowski one or Manhattan distance, which is the sum of these red lines. We also have actually Mahalanobis distance, which is one of the distances which account for correlation between properties. And there was this great question from the previous talk, whether we account for the correlation between properties. It depends on the distance. There are distances and preprocessing which could take care of correlations between properties. So which distance is to be used is of course important. There are many more similarity measures than we have explored in Gracious, but this is what we have decided to explore for the Gracious framework. Now back to data standardization and transformation, why this is important. Here is an illustration on the left with the blue histogram. You see this data is very skewed. When we do the so-called power transformation, there are several methods that do such kind of transformation. We can get a histogram which is more balanced, and the whole distribution of the data will be more close to the normal distribution, Gaussian distribution. So in statistics, this is called power transform. This is not one single transform. There are family functions. They are also parameterized, and it has been invented in order to stabilize variance and make the data a normal distribution like. One very well-known transformation is the Boxkov transformation. In reality, it is basically the logarithmic transformation, and depending on the parameter, it could be different. You see the first formula, but also actually you could use the log transformation to cope with this with the skewed data if you kind of don't like to apply the complex formula. In gradients, I suggested to apply Johnson transformation because it can be applied to 0 and negative values, so we don't need to think what to do with logarithms with negative values, etc. But this is not the only choice. Basically, you need to apply transformation in order to make the data to cope with the skewness of data. So this is what I'm going to. I'm not going to do online demo for the Jupyter Notebook and programmatic database access. This is just to illustrate that this is also could be done. In fact, all the pictures which Wendell showed with Similarity Matrix are generated this way, and we have an open source library by Nanomapper to access the database. You could, for everybody who is familiar with Jupyter Notebook and Python, this should look familiar. There is a REST API, and once we're using these tools properly, we can extract data from the database, which I'm showing it on the right bottom corner. And in the next step, we want to do some data processing with this data. The notebook example also shows queries, how to extract the data, study documents from the database. It's nice to use this library if you don't really, if you're a newcomer, you don't need know what the query to send to Nanomapper, because there are some predefined or configurable queries, and you'll actually see what is the query is being sent when we just fill in the function. And for the distances and transformation, one very familiar tool is scikit-learn, and there are existing packages of different distances. What is being used in these examples is the so-called non-Euclidean distance. It's basically an Euclidean distance, but it could compensate for missing values. So this is one of the reasons of using it in several of the case studies, because usually the data matrix has a lot of gaps, and we need tools that can cope with the gaps. And also for the power transformation, this is a library also part of scikit-learn power transformer. You could specify whether to use Boxkov transformation or Yale-Johnson with supply parameters, and it does the work on its own. Now I have a couple of examples where we have been using this Jupyter Notebook to contribute to the analysis for the Silica use case. This is again dissolution data, but for only for Silica nanoform. You see there are also several benchmark materials like parts which have been added by the team. And this is the code, a little bit annotated, which lines are generating the triangular similarity matrix, but also we have found that clustered similarity matrix is giving more insight on how the materials are grouped. For example, we see this, you can read this across rows and see if the same pattern is across the row, that the materials are similar. And on the right, what you see is a data frame, which is data extracted from the database. Again, dissolution similarity, what we do for the silica use case is calculating similarity property by property, and then combine the individual descriptors, and we have dynamic dissolution with two fluids. You see the and also two different descriptors, half time and dissolution rate. Of course, as we can expect, the similarity matrix for each descriptor is similar, but for the different fluids, they're slightly different. And then we combine them in one matrix. This is again clustered matrix where we can see that the benchmarks, the quartz and minusyl are practically the same. And then we have different groups with aerosyl and zeosyl and so on. I will not go into interpretation of this because this is Hedwig's reporting on this on the silica use case study. Just for illustration, how we generate these charts. And of course, the final slide is a disclaimer that the Euclidean distance doesn't cover everything. It's for comparing scalar values. When we have dose response, we need to introduce some types of dose response similarity or extract a single value from the dose response curve, like for example, loss effect level or similar. In the similarity team has been working on this, and there are actually 3 novel methods for comparing dose response similarity. This is just one of them. Basically, we can generate a distance matrix out of dose response curve as well. And if you have time, I'll do an online demo for a couple of minutes with the file I have been starting in. This is, I need to log in first and click on the similarity. And we have a predefined screen for the white paper similarity here. But also we have a user data option. Here I'm going to choose the file which I have been showing on the first slide. And then this is what we see. This is the dissolution, the first line. Yes.
Nina, we can only see your PowerPoint presentation at the moment, so I think you need to stop sharing and then reshare the new application.
You're right. So stop share, and I'll share screen with the browser. Okay, with the browser. So I go. Share screen with the browser share. Okay, so you see the browser now?
Yes, thank you.
Okay, so I'm going to the nanosafety data interface, which comprises several Nanomaterial databases, and going to the Gracious database. There is a new tab for similarity, and we have a predefined screen this of Gracious white paper data, but also new option for providing user data. And you could download the demo file right here and see this is the file I was showing in the first slide. And then we can upload the file with the same format here and explore the similarity matrices. So if you have your own data, you'd like to try this, please go on. So first 2 lines of dissolution, dissolution rate and half time. Then we have the combined dissolution here. Then we have different property. This is dustiness. And then we have inflammation from 3 different descriptors. And combine it as well, inflammation, and then we have different similarity matrices for reactivity, and also I think the combined for reactivity is this one. All this data is described in a white paper, discussed with even with 2 more different methods. The reason of this demonstration is that there is an easy way to try your data for similarity assessments. So I think I'll stop at this point, and happy to take question or discussion.
Thank you, Nina. So there aren't any questions for you in the chat, but maybe I could just ask a couple of things myself. So you described to us sort of an extension of some of the methods that Vendel was talking about, and maybe it would be worth clarifying between people what the difference between the gracious framework and using the framework is versus going into eNanoMapper and doing a similarity assessment. So what can the eNanoMapper do and what can it not do? And vice versa, what can you do with a framework and what can you not do with a framework?
This is a good question. So eNanoMapper, or just any tool that does data analysis, can calculate similarity between with a data matrix you provide. But the framework, gives advice which properties should be considered according to specific hypotheses. And this is the added value of the framework, which is guides you which properties important for specific effects or specific behavior of the materials. Otherwise, there are many tools that can calculate similarity or by using any descriptor. But what the frameworks gives more is which descriptors to use, which properties to consider.
Okay, thank you. In eNanoMapper, when you can do this similarity assessment that you've just shown here, is there any control over the data in terms of where it's come from? So I'm thinking about specifically, instead of just measuring, say, reactivity, does it specify that you can only do a similarity assessment gathered by exactly the same methodology, or does it allow you to compare similarity using different methods for data collection?
Yeah, so I demonstrated 2 things. One is to upload your own file. Actually, you don't upload. This is not uploading to being uploaded to any server. It's purely in browser. So this is for quick check if you have your own data and you'd like to quickly check similarity. Then whether the data comes from the same method and the relevant method, it's entirely up to the user. And other way of extracting data from eNanoMapper through programmatic means, Jupyter notebooks, or maybe R. There also are libraries for getting data from eNanoMapper. Then you need to pay attention to annotation and to metadata. There's because we're using templates for getting the data into eNanoMapper. There's a lot of metadata around the material, around the actual assay results, and when retrieving data programmatically, we should pay attention to this.
So I think this is an important point. So you could do exactly the same method in the lab. So you could use exactly the same protocol with different materials. But then lab A may choose to normalize the data in one way and present it per milligram of protein, whereas another lab might choose to present it as percentage. So you even have to go down to that level of data analysis and how you produce that metadata in order to make sure it's the same, identical between your different sources in order to do that data analysis. So yeah. I think that's one of the advantages of the framework, is it will stimulate you to make those checks. And whereas when you're doing it in eNanoMapper, it's a really nice, quick, convenient way of doing it, but the onus is on the user to make sure they have made those checks. Okay.
Yes, indeed. It's. I will repeat that the framework added value is that it recommends properties for specific assays and guides the user.
Yeah, great. Thank you very much, Nina. That's brilliant. We are perfectly on time, so thank you to all of the speakers for keeping to the time today. We now have a 10-minute break, and we will start back at 1600 Central European time and 1500 UK time. Thank you very much. We can start.
Okay, I'm sharing now. And it should be on. So thank you everyone for being here this afternoon. And I will start right on presenting the inclusion of the blueprint that Ralph previously presented you into the SANS decision support system. I'm Alex Zabeo from Green Decision. We are a spin-off of Ca' Foscari University in Venice. We've been working on this. So the SANS decision support system is there since long from previous projects. We have two separate areas, one for consumer products and the other one for medical devices. So inside the consumer products, we can create different projects to work on. I prepared this simple example to be brief. So nano titanium dioxide. I can enter the project. Then the DSS allows for 2 levels of assessment. So we will dive into the tier 2 level assessment, so a bit more specified. So this is a risk assessment tool. So we have several models and ways to do risk assessment and to check for the results. But what we want to see today is the integration. So in this, this is a scenario basically. So we are talking about the drilling of the nano titanium dioxide. And if I go into the details, you can see I associated nanomaterial to this scenario. And I can now move on to the characterization, which was present in SANS beforehand. This brings me to a second part of the tool, where I can specify something similar to what you've seen this before and with Ralph. So this is the same implementation, the implementation of the same aspect. So we can specify the type of nanomaterial, its components, the different layers. We can, of course, classify. In this software, we are using trees for classification and characterization. So in this case, I specified some classification state, like being solid and elongated. And then if I move on to the characterization part, in this characterization tree, you can see we have several characteristics. So in this case, instead of inserting numbers, you can choose among classes. And these classes are utilized in the IATAs, for example, to take decisions where thresholds are known. Of course, you can also input data directly if you have more precise data. So like in this case, you can see we can include different category endpoints, all the ones included in the blueprint. So for example, aspect ratio shape, and then we have the different assays and endpoint results that we can input in the tool, and we can specify different descriptors and values. And of course, we can also move on and add other on the same category endpoint and include all the data in this part. Of course, we can also create scenarios. I already created a human inhalation scenario here, but it's not interesting to go into this now because we need to see a lot of things. So if we move to the IATA part, this is the same result that you can get with the testing environment. So you see the different IATAs here with their state. And if we enter an IATA, we have all the different questions that you should answer to. We can select different tiers, like we did, like you've seen in the other presentation. For each tier, you have the introductory text and the different measurement and assays that you might use to get information related to that tier. So also in this case, we are missing information. If I click on the link, the input page appears here, where I'm already brought to the right position, so the category endpoint, the assay, and I can just input the values here. And they are directly imported in the table. So another interesting thing here that is present in the blueprint is the connection with the Gracious Wiki. So once I have to select an assay here and an endpoint, I can just click on this button, and I'm directly redirected to the Gracious Wiki in the definition of the specific endpoint. Now, the Gracious Wiki has now become part of the Terminology Harmonizer, which is a bigger project. And its basic idea is to have the possibility to agree on terminology in general in different fields. So one of the implementations is for the Gracious project, and the Gracious Wiki is what you're seeing now. We can have several knowledge bases. These ones are derived from the blueprint that was presented before. And if we open a knowledge base, we can see a list of its components, like in this case. And for each level 1 endpoint or category endpoint, we can open up and see all the specific endpoints contained. When we click on an endpoint, we get the current definition for that. So let's suppose you have something to say about this definition. You can up or down vote it. And this is used in order for several experts to agree on the fact that this is the correct definition for the complete control, for example. We can add a new comment here, so that now all the users can see this, and of course, the person in charge of the definition can take it into account to modify the definition. In fact, the system is based on a moderation infrastructure. So let's suppose I am a user who is an editor, because you can have different roles in the tool. I can simply propose a new, we call them enumeration to be generic. In this case, we are talking about category endpoints, for example. So I name it new category endpoint. I can propose my initial definition and add it to the system. So what happens now is that if I filter out and go to the proposal, you can see my new proposal is here. It is the only one labeled as a proposal. And now, because I am a moderator, I can go to it, read the definition, add my comment. I can approve it or discard it. And if I approve a definition, it becomes a candidate. So now you see it's a candidate for the system. It is also included in the complete list. If we scroll down, you can see it here. And so it will be a candidate. It is available for everyone now to comment. And it will be included in the new next iteration of the blueprint. As you can see, we have all the versions of the blueprint here. So what happened in Gracious is that the moderators take into account the candidates. They were included in the blueprint. The blueprint JSON was generated and then imported again in the Gracious Wiki to generate a new version where the previous candidates become new items, and they are labeled as new or updated if something has been changed. And this allows to agree on definition and continue to work on them during the project and in several categories. Moreover, the tool allows to work without any blueprint, so you can just start from scratch and create your knowledge bases, categories, and endpoints, or whatever you want to agree upon. Use the tool to get to a specific definition. You can also specify sources of information, like this comes from an ISO. You can specify the title and the location, for example. And this will be included, and the user will be able to link and go to the ISO to see what we're talking about. Then I guess that's all for me. Also, the time should be finished. Thank you.
Thank you, Alex. That was great. So that was a really useful. So Ralph earlier on showed us the blueprint itself, and he showed us how we tested it in an online test environment. And then Alex, that's a really nice demonstration of how the blueprint has been incorporated into a different piece of risk assessment software, in this occasion, the Sun Decision Support System. So it's exactly the same blueprint, exactly the same software, but being utilized via a piece of risk assessment software. So thanks, Alex. That was really useful. And then how it links to the wiki. And I believe the wiki is feeding into other projects, perhaps in the OECD. Is this correct?
Yes, Tiki. Basically, it's used in Sunshine, and it's also in this moment used from the nanosafety cluster in Sabina and also in NanoPub.
Okay, that's great. Thank you. Okay, so thanks, Alex.
Thank you.
So now we have Gian Pietro, and Gian Pietro is going to talk about the, I mentioned it earlier, but didn't say that he was going to talk on the data quality and completeness methodology that's been generated in Gracious. Thank you.
Hi everyone. Hi Vicky. Can you see my screen and can you hear me?
Yep, perfect.
Perfect. So yeah, as you said, we've proposed in the Gracious project within package 6 the data quality and completeness assessment methodology. Starting, we had some objectives. First objective was to develop this methodology for assessing data quality tailored to risk assessment purposes, and to implement it in the Nanomapper database. Moreover, we wanted to test it on a weighted evidence approach, which is now under review in NanoImpact. The methodology focuses on physicochemical and ecotoxicological data. And in this methodology, data quality and completeness are assessed in such a way that all the required steps of the methodology are automatized. So we want to have a minimal reliance on expert judgment. What about our approach? We started with a literature review on current data quality and completeness criteria and approaches. We created a small working group to develop the methodology, which is basically me, Nina, Hubert, and Daniel. And we started implementing it in a Nanomapper and moreover in the weight of evidence approach, as I said before. After the literature review, we selected 4 criteria for evaluating data quality, which are data completeness, which refers to the degree to which all required metadata associated to a study in a dataset are available. Data reliability, which measures if the study has been conducted in a reliable manner. Data relevance, which measures if a study was conducted using standard protocols or procedures. And data adequacy, which defines the usefulness of the data for the specific task, in the particular case for risk assessment purposes. Data completeness, so the first criteria. We started from the approach proposed by Comandella in the frame of Gracious project. This approach is to assess completeness is based on the evaluation of 11 measured relevant physical chemical properties, which are crystallinity, composition, particle size, specific surface area, surface chemistry, particle shape, surface charge, surface hydrophobicity, density, water solubility, sorry, and dustiness. Most of these these physical chemical properties are recommended by ECHA for grouping and read across. Some of them are also required by REACH for nanoform identification, and moreover, most of them were the initial set of parameters initially proposed by Gracious for the IATA. These properties are again either required by REACH or by ECHA for grouping and read across, as I said before. Completeness score is based on the Nanomaper templates that Nina will show and Hubert will show to you in the next presentation, and is computed as the number of items, so parameters reported on a specific template, then divided by the number of items required by the templates. And the final completeness score is the average between the completeness scores of each template. We propose to adopt the same approach also for evaluating completeness with respect to ecotoxicological templates. Here you can find an example, but Nina will probably say more about this. This process can be automatized directly in the templates. And indeed, as Nina will show to you, it has already been implemented in the Nanomapper database, as you can also see on the figure. An important thing to say here is that we can weight different parameters in the template more, and in this case, expert judgment is of course needed to set up properly this weight. Data reliability, on the other hand, is usually done by means of the ToxR tool, which is the state-of-the-art tool for assessing reliability for toxicological data. It assigns data to 3 categories, which are reliable without restriction, reliable with restrictions, and not reliable. Moreover, there is an additional category which is not assignable, which should be made, and studies within this category should be made by, assignments shall be made by direct consideration by the user. For ecotoxicological data, on the other hand, there is the CRED tool, which is similar to the ToxR tool, but adapted for ecotoxicological data, and both tools are based on the CLIMISH score for evaluating data reliability. The main drawback of these approaches is that the requirement of such tools requires expert judgment. However, what we found is that most of such requirements are already considered when evaluating completeness of data. And this suggested us that if data is sufficiently complete, it is also sufficiently reliable. And for this purpose, and for this motivation, we decided to merge the 2 criteria, as having an high completeness score also implies, or also should imply, a higher reliability of the data. The third criteria that we selected is data relevance. Relevance covers the extent to which data and tests are appropriate for other characterization, and it basically answers the question: is the study conducted using protocols and procedures that are relevant to the specific task? We selected 4 categories for data relevance. The first category is data derived by means of international recognized standard guidelines, such as the OECD's testing guidelines, but not only this. The second category is data derived using nanospecific validated protocols and protocols which are candidates to become standard protocols, such, for instance, the OECD testing guidance with modification. Third category is data for which the protocol is not included in the first 2 categories, including nanospecific protocols which are not yet validated. For instance, the protocols which are being proposed in a European project, but one day will become standards. The last category is data for which the adopted protocol is not reported or in the study or in the original source, in data source. This step can be automatized by providing a predefined list of protocols, and indeed in Nanomapper this is the case because we already have a list of possible protocols used related to the templates for reporting data in Nanomapper, for data reporting in Nanomapper. Last criteria is data adequacy, which defines the usefulness of data for the purpose of the analysis. In our approach, a higher weight is associated to the most reliable tests for risk assessment purposes, again, which are in vivo tests, while slightly lower weights are associated to in vitro, and even lower weights are associated to in silico studies. So at the end, we have 3 categories. The proposed methodology for data completeness and quality assessment is again, and this is something important to remark, tailored specifically for risk assessment and takes into account the 4 identified criteria. The scores are computed for each criteria and then aggregated by a mathematical average into a data quality and completeness score. This process can in principle be fully automatized, highlighting data quality directly on the database user interface and on the templates when uploading or downloading data from it. The data quality and completeness criteria may then be assigned to a specific light into the traffic light system, as Vicky was mentioning this morning, based on a predefined thresholds, where we will have a green light for data of high quality, yellow light for data of sufficient quality, but which needs further consideration to be used for the specific task, or a red light when data is of insufficient quality. Alternatively, we can show the data quality and completeness score to the user by using by means of a continuous scale. This work was proposed to a workshop at the end of June, specifically on the 28th of June, on a virtual workshop, which was open to a lot of stakeholders, mainly from the academia, but also regulators, consultants, and non-governmental industries and not governmental organizations participated on it. Specifically, more than 80 people, mainly from Europe, attended the workshop. During this workshop, we gave several questions to the attendees, and we found that many tasks, many activities require data quality assessment in their work, specifically other assessment and work on, and in general, working with toxicological and ecotoxicological data required data quality assessment, of course, but also risk assessment, other modeling, other characterization, and so on. From this workshop, we got a lot of inputs. For instance, one of the inputs was that the increased amount of metadata associated to physical, chemical, and toxicological endpoints will require updates to the current templates, so to the NanoReg and Gracious templates. They said that the weights, as I said before, should be customizable. And most important, it is needed to demonstrate with real data that reliability and completeness can actually be merged. Moreover, we of course will need to regularly update the categories for data relevance, so the testing guidelines which are standard and the one which are candidates to become standard. We also should consider adding advanced in vitro studies for adequacy, and we also should consider linkages to adverse outcome pathways. Moreover, we should consider the applicability domain and data representativeness as additional criteria. Finally, further work is needed to understand if the proposed approach, which now is currently tailored to risk assessment, can be adapted also to other tasks. So in summary, traffic light methodology for assessing data quality and completeness has been proposed in the Gracious project, and this will be further developed and further work will be made on it also in the other NMBP 13 projects, which are NanoRigo and RiskOn. The approach is tailored for risk assessment purposes and focuses on physical, chemical, and ecotoxicological data. And the methodology has already been partially implemented in Nanomapper database and on a weight of evidence approach, which is currently under review in NanoImpact. So this was my last slide. Thank you for your attention.
Thank you very much. That's really great. I don't think there are any questions for you in the chat at the moment. So if I can just remind the audience, if they do have any questions, please pop them in the chat and we can address them later on. So Gianpietro, if you could stop sharing your screen, please. And our next speaker, I think, is Hubert. So Hubert's going to talk to us about the templates that have been generated during the Gracious project. Thank you.
Hello, everyone. First of all, can you see the presentation well on screen mode? Thank you. So I'm Hubert Rauscher from the JRC, and I'm going to present you the last piece of information coming back to the templates for logging of data already mentioned by Gianpietro before. And this is the work of many people, many experts from the Gracious project and beyond, of course. It's a collaborative work. Now, I'm trying to, okay, so now, why do we use, or do we need, or why has the project agreed on using templates for reporting or data logging? As you saw before, in all the presentations, this Gracious framework for grouping and read across requires in many places very detailed, complete and comparable data of high quality. And furthermore, so these data need to fit together so that you can run through the IATA. Furthermore, all these data from the project used in the project come from a variety of different fields, such as physicochemical data, ecotoxicity data, exposure data, and also from a variety of different sources, or from different project partners, or even from outside of the project, from existing databases. So these data and the availability of this data, the reporting, at least in the project, it needs to be done in a way that allows to reuse these data for other purposes in different IATAs, and also maybe they should allow some quality assessment of the data. And therefore, project decided to use harmonized templates for data reporting to be used by every project partner. Now, this of course is not the invention of the Gracious, this principle, but this is fully in line with the FAIR data principles. FAIR data principles, you can see them here. And one of those principles is that the data should be reported in a common harmonized format that require a minimum set of information. And this is exactly what the templates do. It is also possible, you will see, to, let's say, within a limited framework to assess some aspects of the quality of the data using such templates. And if you would like to know more about the FAIR principles as used in nanosafety databases, please have a look at the paper by Nina and co-authors. Now, so coming back to these templates. These templates originated in an earlier project called NanoReg. Many of you may know this project that has been concluded quite a while ago, where there were some templates for reporting of data regarding endpoints that are thought to be relevant for safety assessment of nanomaterials are collected. So because this is fundamental for the safety assessment of nanomaterials, you have complete data sets with the metadata needed. And so starting from the project NanoReg, they developed such templates. And the templates themselves, they have a quite simple structure. They are based on Excel spreadsheets. When the structure you can see here. So they consist basically of 5 sections, you can see in the first line. Information about the sample itself, then information about how the sample was prepared, information about the method and the instrument used, on the results and the SOP used. And then you have a number of columns. How many columns these are depends on the exact endpoint or property to be reported regarding information on the sample itself. So batch number, sample preparation, how it was done, what method has been used, which instrument, what the settings, and the results, detailed reporting of the results and the used SOP. Then when you have this, you can insert in every row R1 to Rn one experiment, the results of one experiment with a complete data and metadata set. So then, and you can report several experiments results in one template, but each of the template refers to a specific property and technique. For example, in physicochemical part, size distribution as measured by electron microscopy. And quite a number of, well, some templates were available from the NanoRec project, but not all that were necessary for Gracious. So those that were not existing from NanoRec have been developed within the Gracious project to serve the specific needs and the specific information requirements from Gracious. And that refers to physicochemical data, but also to ecotox data and others more. And the advantage of having such simple templates, so the Excel sheets, is that they can easily be machine read, so they can be read in databases, as for example done already in the eNanoMapper database that Nina will show you later on. So now, how does such a template look like when it is filled? Just one example, zeta potential. For the zeta potential, you have these different sections as reported before. So the sample information, a lot of information items. You don't need to read this, but this are all these information items necessary. For the sample information, then method and instrument information, results, and the SOP, you cannot see it anymore because it is. And then you can see here in these rows, the metadata for a single experiment. So this way, every project partner that is reporting results on a specific property or endpoint can use this data, and they are then comparable with results reported from other partners. And also they are compatible or in line with the different, let's say, properties or endpoints required. And you can read the story about the templates in that paper by Comandella et al. But what you can do besides reporting the data in a harmonized way, you can also use the data to evaluate some aspects of data quality. For example, here, very simple data completeness. When we say, okay, there is a certain number of items required to report completely the results of one experiment referring to a specific endpoint. This would be the number of items required, and that the items, the number of items reported actually is written here, and then the quotient, the ratio could then be associated. Would then be a completeness score that goes from 0 if nothing is reported to 1 if everything is complete. And this way, the completeness can also be evaluated as one aspect of data quality and one aspect of the fairness of the data. But we can do more. One could calculate completeness scores on different sections. If you're interested in that, in these sections, or one could also associate weights with the different information items. So if you think one specific information item is more important than others, one could associate a higher weight, and this way give it a higher weight in the completeness. And this has also been done already in the Gracious eNanoMapper database implemented by IDEA Consult. So now, which templates are there and where can they be found? Now, I referred now mainly to the physical-chemical templates, but there are more, not only physical-chemical, but also human health templates. And the Gracious developed more templates referring to in vitro endpoints, ecotox endpoints, exposure and release endpoints. Now just here the summary where they are. So the nanoreg templates in their original form, they are publicly available on the JRC server, so everyone can access it, download it, and use it. And the Gracious templates, so those templates that were made in the spirit of the nanoreg templates, but for which properties templates were not existing but needed for Gracious, they have been developed. They have very similar structure for the PhysChem part, for example, surface chemistry by XPS, and they are available for the PhysChem part also in the JRC publication repository, publicly available. Plus, in the meantime, there are also exposure and release data templates referring to exposure and release. They are on Zenodo, also publicly available. So the structure of these is a bit different, owing to the different requirements in the exposure and release field. So you can have a look at those. They are done in the same spirit, but having different information items. And then there are still more templates regarding the in vitro assays and other assays, but they are not yet publicly available, but they are available to specific projects if they are in the eNanoMapper. So you can go, if you use the eNanoMapper, into this search window of the eNanoMapper, and then you find some project, and if your project is among them, for example, Gracious, you go there and you locate a so-called template wizard, where you then find all these templates that are available for a specific project. But Nina will elaborate more on this. So I'm already done with this part, but I just would say that agreeing on harmonized, having harmonized templates that are agreed, of course, this is something very valuable. And I have to say the hardest part is to get not to get an agreement of templates. This is not easy, but to make people use the templates, because then when you have the data there that are in these templates, you can do so much more with the data, and then this means then they are comparable with each other and interchangeable and reusable. So the proper use, I would say, the final sentence here in my part, proper use of well-defined reporting schemes for experimental results can increase the metadata completeness and also ensure their comparability, integration, and reuse for further purposes. And here I would like to stop with my part and hand over to Nina, who will explain you how these templates are implemented in the eNanoMapper and how they are, how you can use them there. Thank you.
Thank you, Hubert. Do you see my screen?
Yeah.
Yes, we see.
Okay, thank you. I will, I have slides, but I'll switch directly to the online demo for the sake of time. And thank you, Hubert, for pointing to template wizards. Actually, we have templates not only for the projects which protected, but there are several publicly available eNanoMapper databases, and they also have template wizards. So if the templates are publicly available, they will appear there as well. But for now, what I'm going to demonstrate is the template wizard within Gracious, And here we go for the template wizard, and we see that we have many templates which have been gathered and developed by different projects. Now we can filter them like FISCAM in EcoTalks and exposure and release. We have also metadata templates for mixed metadata. I would like to go to the gracious templates. Hubert explained with very detailed for FISCAM templates, and we also have those response templates developed by a gracious partner, mostly work package 5, and of course we have this is really new development for release, environmental consumer release and occupational release, which are also available on Zenodo. So let's go for the FISCAM template. Hubert started with Zeta potential, and I'll go for Zeta potential template as well. The template wizard is basically a web form which allows you to configure a little bit and download the configurable template. So if we going to report Zeta potential within Gracious project, this is work package 3, and maybe we'll go for some of the partners who did experiments in work package 3, and one added value of the template wizard compared if you download templates from GRC or Zenodo repository is it's customized for with the materials which used by the project. Then when you download the template and we open the Excel file, okay, I would like to enable editing. On the first sheet, you see all of the acknowledgements, and then we go for the Zeta potential fields. But we also have a list of materials which are agreed to be used in the project with well-defined names. And when you use the material, you need only to do drop down, and this alleviates the need of remembering the name, and will help us when we import the data, because otherwise we have been experiencing many different spelling of the same material. So I'm not going to details of these templates because Hubert has been explaining it a lot, and we go back to the template wizard. And we'll go for some of the in vitro templates. For example, this one, this is a dose response template for cell-based assay. Most of the in most of the templates, there are different parameters to explain, but also what is important is when we change the number of replicates and technical and biological replicates, we'll have automatically generated layout. Of course, we can also search for cell name. And yeah, okay, we have a cell name, and for SOPs available, and all the parameters you see could be changed, including the concentrations, the units, the number of materials, if you like, controls, etc. And of course the partners. This is developed by BFR partner, and this has been in work package 5. Again, we have all the list of the materials, and then when we download the template, we obtain Excel file with a different formats. This is format originate from the developments of IOM, the Institute of Occupational Medicine, for the last 10 years or so, which was being led by Peter Ricci and now Shahzad Rashid. It has a different structure. Some of you are well familiar with this template. What I would like to show is that we here have again drop down for the material, and we could have several materials here, and then we have sheet for raw data and results. And in the results, we already have formula specified when we have been developing these templates together with BFR colleague. She specified how the formula should look like, how the normalization is done, and so on. And basically, when you fill in your data, then all you need is to fill in raw data, and then it is being automatically calculated. This is the template for one of the templates for dose response. I would like to also to show the templates for exposure and release, which are also developed by work package 2 in Gracious. As Hubert says, they're a bit different, and we can choose one or the other here. We have integrated lookup for echo use descriptor. You don't really need to select anything here, but if you select, then you'll have not all of the descriptors, but just the ones you need. Also the same for activity, etc. And then we download again these templates. We also have the materials integrated. And this template has integrated quality assessment, which is different than the traffic light methodology explained by Green Decision. This was developed by the exposure experts. So we have again the first sheet, but then with the information, and then we have all this template with the fields agreed within Gracious Work Package 2.
Nina,
And
Nina,
yes,
I see a blank screen at the moment.
Yeah.
I don't see a template.
Okay. This one. This one. Now, do you see it now?
Yes, thank you.
Yes, so this is the exposure and release template. This is occupational release template developed by Work Package 2 in Gracious. And I really hope this will be a step forward to for harmonizing exposure data, which has not been done before. This is a brief overview of what I wanted to show for the templates. What I would like to say with the templates is all of these Gracious templates, they have been already shared with a number of ongoing projects, and they are being used in all these projects and being also updated. For example, in one of the projects, people are using not WST1, but WST8, but they are happy to use the same template. And all the FISCAM templates are also used by other projects, and actually some of the Gracious templates are now being improved in some of the ongoing projects. So there was a great question from the beginning whether there is a divergence in the templates. Well, yes, there is, but with this template wizard, we're trying to get hands over it and to make it controllable. So even if there are improvements, we can make it, we can annotate it in a harmonized way when importing to the database. What I would like to finalize with is these templates are data entry for the Nanomapper database, but they could be used elsewhere as well. We have published this workflow, how we take the spreadsheets and convert them, import them into a FAIR database. There is an open source software that does this, which this paper was published last year, and yeah, this is a way to do collaboratively enforce some harmonization on data reporting. And I'm happy that this is being used in many ongoing projects.
Thank you, Nina. We have a question from Elisa Moschini in the chat. Do we need to have a specific agreement to have the opportunity to use these tools within other projects?
So for Nanomapper database, there are several, I can answer for the Nanomapper database. There are several openly available instances of Nanomapper, including the template. So this could be used by anybody. Otherwise, if you'd like to have a private instance of Nanomapper for some of the projects, this is usually decided within a project, and there could be an agreement. Otherwise, for the blueprint and the wiki harmonizer, maybe Ralph and Alex or Daniel could comment.
Yeah, Ralph here from ThinkWorks. As far as concerned the blueprint, the PDF will be public on Zenoda, so it will be publicly available. So that's and the design environment will be made available for partners interested in integration of the blueprint in their software, so that they have examples how to do that.
So, Ralph, what about the Guide Nano tool? How, if people wanted to use the read across functionality of Guide Nano tool, how would they go about accessing that?
The Guide Nano tool is currently being further developed within the Sabina project, and perhaps it will become part of the Sabina overall framework. So we have to decide how to open that up, but an older version prior to Sabina is available, and you can just ask a link. Credentials for it to access it, but it does not yet contain, of course, the new similarity part, which we tend to work on in Sabina. So that will be a few years before that's in there.
Okay, and then Alex, for the Sun Decision Support System, if people wanted to access the grouping and read across functionality in the Sun Decision Support System, how would they do that?
Yes, it is now we are completing the development. So what you've seen is in the development server, but after the end of the project, it will be migrated to the official SANS website, so sans.gd, and you will find it there already. And then for the terminology harmonizer, it's also open to look into projects. So you just open it and ask to the project owners to be included, and this is done in the tool. And if a project wants to use the terminology harmonizer, we are open usually, but again, we need permission from the project partners to use this tool for others, but it's usually we open it up for anyone who asks to use it.
Alex, please could you put the links for those things into the chat, please? And Ralph, could you put the link for the Guide Nano existing tool into the chat? And maybe Ralph, if you could put and Alex, if you could also put your email addresses in there as well, so that if people want to get access to those versions in the future, they have your contact details. And then Nina, for the wizard, the template wizard, how do people access the template wizard?
They could go to the nanosafety interface at search.data.nanomapper.net, and if they are not part of particular project, they could go into the public projects, which Nanorec 2 or Nanomapper. They are all completed projects, but they all have the publicly available tools there, so they could go for the template wizard there.
Okay, thank you. So Nina, if you could pop that web link into the chat as well, that would be really helpful. Elisa, does that answer your question in completion, or were there any other aspects that you wanted to access? Elisa, I think you can open your mic if you want to speak.
Okay, hello everybody. I was just wondering if there was the opportunity to contribute in feeding these tools with the results coming from ongoing projects that are always NBP 16 projects, but for example, not there are no common partners between the projects.
So there are internal common partners in all 3 NMBP 16 projects. So in Sunshine, we have myself at Heriot Watt and others at Heriot Watt. Green Decisions, so Alex and Daniel are involved in Sunshine, well, helping to coordinate it. Also RIVM are involved, and I think JRC as well are all in Sunshine. Harmless has BASF and BFR, they are all involved in that project. And then Diagonal has fewer links, but we do have an agreement for the 3 projects to collaborate with each other. And on Wednesday of this week, we will have what we've called an ambassadors event. So we've identified key ambassadors to link the 3 projects together. And that will include ambassadors for grouping and read across, and for data management, and for templates. So there is an agreement between those 3 projects to do that.
Okay. It was just to understand, let's say, the limit of this agreement, but it's perfectly fine. And I think I will join the event.
Brilliant.
From Diagonal part. Okay.
Excellent. Thank you. That's really good. Okay. Have I missed any questions in the chat? Is there anything that's not been addressed? Please speak up if anyone thinks I've missed anything. No. Okay. So Judith has provided links to the Gracious guidance document in the on the Gracious website. There's a link there for that. The nutshell version isn't on there yet, but it will be finalized in the next couple of weeks or maybe even days. There's just the final edits, checks, and it's more formatting just to make sure it looks professional, and those will be available in very, very soon. What I suggest we do, Judith, I don't know if you can help me to do this at the end of the meeting, is compile all of the links that have been provided in the chat today into one document, and then we can make that available to people after the call. Would that be okay?
Yeah, I think so. Fine.
Okay. So I would like to thank Judith and thank all the speakers for today, and Stella and Hildegard and Visa and colleagues for helping to organize today. And thank you everybody for listening and for your interesting questions and your participation. Tomorrow afternoon, starting at the same time, so 1 o'clock UK time, 2 o'clock Central European time, Andrea Haas will host a workshop which will go through some of the case studies where the Gracious framework has been employed to assess the similarity of a range of different types of nanoforms. And then on Wednesday afternoon, there will be the ambassadors event, which will be a discussion between Diagonal, Harmless and Sunshine on some of those collaborative activities, including the grouping and read across that will progress after the end of Gracious. So thank you everyone for a really interesting meeting today. Thank you for your participation, and I look forward to seeing you tomorrow.